Hi everyone! In this video we're going to start chapter 8. This is focusing on the different states of matter, so solids, liquids, and gases, specifically what holds them together. So those are called intermolecular forces. And then in the second half of the chapter we're really going to focus on gases. So on this chart, you'll notice we have a solid, a liquid, and a gas. And up above, we can see we have increasing kinetic energy. So Ke is kinetic energy. And this is related to temperature. So if we increase the temperature of a solid, it eventually melts into a liquid. And then if we keep heating the liquid, it eventually turns into a gas. So we already know that. But down below, I have increasing IMF. And IMF stands for intermolecular force. So inter means between, and intermolecular means between molecules. So this is a force that exists between molecules, and that force can hold those molecules together. So obviously, intermolecular forces are going to be much, much stronger for solids, where molecules are held very tightly together, versus liquids where, they can move around a little bit. And then with gases, intermolecular forces are very, very weak. So those gas particles or molecules are no longer close together, but very far apart. All right, so kind of diving more into intermolecular forces here, or IMFs. So we've seen that temperature can affect when substances change phase, so when they go from solid to liquid to gas. Pressure can also affect the state of matter. So for example, you could apply a lot of pressure to carbon and eventually form a diamond. So same thing here with a liquid, you could apply pressure and potentially form a solid. Now each substance has its own unique melting and boiling point. Why is that? So this again has to do with the intermolecular forces that exist between molecules. So if we look at hydrogen gas, for example, hydrogen gas mostly exists as a gas. So at most temperatures, it's a gas. And you'll even see here that hydrogen gas can't really form a solid unless we freeze it down to negative 259 degrees Celsius. And then hydrogen gas exists as a gas above negative 253 degrees Celsius, and that's still a super low temperature. Now, the reasoning for this is intermolecular forces between hydrogen molecules are really weak. So hydrogen molecules don't want to hang out with each other. They want to be far apart, doing their own thing. And so hydrogen mostly exists as a gas. If we look at water, H2O, water will freeze at 0 degrees Celsius and boil at 100 degrees Celsius. So we've seen that before. So compared to hydrogen, water has stronger intermolecular forces. So it does exist as a solid, it can exist as a liquid, and it doesn't exist as a gas until 100 degrees Celsius. Now, if we look at sodium chloride, NaCl, which is just table salt, this is a solid below 801 degrees Celsius. So that tells us NaCl is pretty much always a solid at all temperatures. We would have to hit 800 degrees Celsius in order to see it melt. And then the boiling point for NaCl is 1,413 degrees Celsius, So again, the intermolecular forces for sodium chloride must be super strong because it takes a ton of energy to melt NaCl and then eventually boil it. All right, so again, boiling and melting points for a particular substance depend on the strength of those intermolecular forces that exist between the particles of that substance. So there are a few different intermolecular forces that we're going to go through and talk about. The first one is called a London dispersion force. Sometimes this is referred to as a van der Waals force. It just sort of depends on who you're talking to, basically, but we'll refer to this force as a dispersion force. The next intermolecular force is called a dipole-dipole force, and this is a little bit stronger than London dispersion forces. Next is hydrogen bonding. This is a bit of a misnomer because there isn't actual bonding going on. This is still just an intermolecular force. It's not a covalent bond or an ionic bond. So we'll put that in quotations. It's hydrogen bonding, quote unquote. But that's going to be stronger than dipole-dipole forces. And then last but not least, we can actually consider ionic bonding an intermolecular force. So this is our strongest intermolecular force. And we've already talked about ionic bonding. So before we get started on London dispersion forces, I just want to talk a little bit about different types of forces because right now we're talking about intermolecular forces, but there are also intramolecular forces. So intra means on the inside, so within a molecule. So intramolecular forces are very, very strong. So this would be something like a covalent bond. So this is going to be even stronger than intermolecular forces. Now, again, in this chapter, we're focused on these intermolecular forces. And again, inter means between. So down below, you'll see we have HCl, hydrochloric acid, and we have 2 copies of that molecule. So if we look at the bond between hydrogen and chlorine, that is considered a covalent bond, which is an intramolecular force. So that's within the molecule. But the type of force we're talking about in this chapter is an intermolecular force. So this is between different molecules. So this is going to be a weaker force than a covalent bond. But again, intermolecular forces do have varying degrees of strength. So let's talk about London dispersion forces first. These are going to be our weakest intermolecular force. Now, all molecules experience dispersion forces. And what this force is, essentially, it's a movement of electrons, and it's an instantaneous movement of electrons. So, for example, let's say we have an atom that has 3 electrons. Now, those electrons are moving around the atom, they're whizzing around, and there might be an instantaneous moment where all 3 of those electrons are on the left side of the atom, just for a very, very brief moment. Now, what this can do is cause a temporary separation of charge, and this will disappear almost as soon as it appears. So you can see why this would be a really weak force, because it's instantaneous, it doesn't last very long, But in that one moment where the electrons are on one side of the atom, we do end up with a partial negative charge, and we symbolize this with a delta symbol. So this is the Greek letter delta, the lowercase version, and a negative symbol next to that. On the side that doesn't have electrons, we get a partial positive charge. Now, what this does is if there are any atoms or molecules nearby, that instantaneous separation of charge is going to affect the molecule next door. So that could cause the electrons from the other atom to be attracted to that partial positive charge, so they might instantaneously move over as well. Now again, this is all going to happen super quickly, so this force is not very strong. Now what if we're comparing atoms of different sizes? So in a larger atom, the valence electrons are actually going to be further away from the nucleus than in a smaller atom. So we've seen this before on the periodic table. If we go down a column, we're adding more energy levels for electrons. So the valence electrons, which are the outermost electrons, those are going to start getting further away from the nucleus the larger the atom. So those valence electrons aren't held as tightly to the nucleus because they're so far away, and they can more easily form those temporary separations of charge, which is called a temporary dipole. Or in other words, larger atoms have more London dispersion forces or stronger dispersion forces. So for example, let's look at the halogens. So we've got fluorine, chlorine, bromine, and iodine. So those are all diatomic molecules. You might remember our acronym Hofbrinkel. So the halogens are within that acronym of diatomic molecules. And notice that as we go down this column, this atomic radius is getting larger and larger. So iodine has the largest atomic radius. Similarly, if we look at the melting points for each of these molecules, that's also increasing as we go down the column. And boiling points increase as we go from fluorine to chlorine to bromine to iodine. So what this actually tells us, down below, fluorine and chlorine are typically gases at room temperature. And remember, gases are going to have weaker forces between them, which is why they're gases. They want to spread out and take up room. However, bromine is found as a liquid, so that means there must be stronger forces between bromine molecules. And then iodine is found as a solid. So iodine must have even stronger forces between them compared to fluorine and chlorine. Now, each of these molecules exhibit London dispersion forces, which overall are very weak. However, if we're comparing molecules within this group, some are going to have more London dispersion forces than others. So iodine, being a really large atom, exhibits more London dispersion forces. And then you can actually see pictures off to the side of chlorine, which is a yellow-green gas. And you might remember that's where chlorine gets its name. Chloros was the original name, and that's Greek for yellow-green. And then bromine is sort of an orange liquid. and iodine is a purple solid. So even though halogens have similar properties, they can look very different. Now, one example of how London dispersion forces can actually become quite a strong force is gecko. So if we were to zoom in on a gecko's foot and we looked at one of its toes, each toe has multiple strands here, or hairs we could call them. And each of these hairs, if we zoomed in on those, has multiple branches. Now, each of these little branches can exhibit dispersion forces. Now, we just said dispersion forces are very weak. However, if you have multiple London dispersion forces that kind of add up together, then you can actually see some pretty strong adhesion. So we know geckos can climb walls, they can crawl on the ceiling, they stick to a lot of different surfaces, and it's because of these multiple dispersion forces from all of these different little hairs and then the little branches on their hairs. So we've got multiple dispersion forces. And I believe that scientists are trying to use this idea to create better adhesives. So things like Band-Aids or, any kind of sticky substance. All right, so now let's go on to the next force, dipole-dipole forces. All right, so again, dipole-dipole forces are going to be a little bit stronger than London dispersion forces, and let's talk about why. So previously we discussed that a covalent bond that has an unequal sharing of electrons is called a polar covalent bond. So for example, if we look at hydrogen and fluorine, hydrofluoric acid, we know that fluorine is more electronegative, so fluorine is going to like electrons more. What this does is this creates a partial negative charge on fluorine. And then we get a partial positive charge on hydrogen, which is less electronegative. So that would be a polar covalent bond. And then a covalent bond that has an equal sharing of electrons. So for example, if we had two of the same atom bonded together, that would be a non-polar covalent bond. So since polar molecules have a partial positive charge on one side and a partial negative charge on the other side, we can actually call this a dipole. Now, if we have two molecules lined up next to each other, we get a dipole-dipole attraction. So for example, down below we have HF again. And we've got our partial negative side with fluorine and our partial positive side with hydrogen. And this creates a dipole. And this is actually going to attract another molecule. So the positive end of another molecule is going to be attracted to the negative end of our original molecule. So our dipoles are going to line up in the same direction. Now, we could also line up our molecule side by side, and a similar thing happens where the positive end of one molecule is attracted to the negative end of the other molecule. So again, this is called a dipole-dipole force. All right, so now that we've talked about London dispersion forces as well as dipole-dipole forces, let's practice identifying if the following molecules exhibit dispersion forces or dipole-dipole forces. So let's start with our dispersion forces. Now, dispersion forces are typically going to occur between nonpolar molecules. And dipole-dipole forces are going to occur between polar molecules. So let's look at N2, nitrogen. So we've got two nitrogen atoms bonded together. And do we have any electronegativity difference between those two nitrogens? No, they have the same electronegativity value. So this would be a nonpolar molecule. And what type of force would we expect? A dispersion force. So, for example, if we had two nitrogen molecules side by side, the force between them would be a dispersion force. And again, this is going to be a really weak force. Now, normally we find nitrogen as a gas at room temperature, and nitrogen exists as a gas at multiple temperatures. And part of the reason for that is the fact that nitrogen is a nonpolar molecule, and so it exhibits very weak forces. So nitrogen molecules really don't want to stick together. They want to be floating around doing their own thing. All right, let's look at HCl. So let's figure out if this is a nonpolar or polar molecule. So we've got hydrogen bonded to chlorine. Now, if you don't have an electronegativity table handy, I can write down the electronegativity values for you. So hydrogen's electronegativity value is 2.1 and chlorine's is 3.0. So if we take the difference between those values, we get 0.9. So would that be a polar molecule or a nonpolar molecule? A polar molecule. So remember, if the electronegativity difference is between about 0.5 and 1.8, it's a polar bond or molecule. So which force would we expect between HCl molecules? Dispersion or dipole-dipole? Dipole-dipole. All right, so chlorine in this case is going to attract electrons more than hydrogen. So chlorine would be partially negatively charged, and that's going to attract a hydrogen from another HCl molecule, and they'll kind of line up and form their dipole-dipole interaction. And this makes sense. We've used hydrochloric acid in lab, and it's typically found as a liquid. So it must have stronger forces holding it together compared to nitrogen gas. All right, last we have carbon tetrachloride. All right, so let's draw the Lewis structure. Let's see, so we've got 4 chlorines that are surrounding carbon, and we've drawn this one before or something similar. Now, in this case, the shape of the molecule is going to matter, so the geometry. What geometry do we expect for carbon that has 4 bonds? Tetrahedral. Okay, so let's look at what that would look like in 3 dimensions. So you might remember tetrahedral looks something like this. So 2 of the chlorines are kind of on the plane of the paper. 1 chlorine is coming out towards us, that's the wedge, the solid wedge. And 1 chlorine is pointing behind the page, which is the dashed line. So all of these bonds are equally spaced. So even if we go through and figure out the polarity for each individual bond, it doesn't matter because all of the bonds are equally spaced, and that will tell us that this is a nonpolar molecule. So, since this is a nonpolar molecule due to the geometry of the molecule, which force do we expect between carbon tetrachloride molecules? Dispersion forces. All right, so again, we can figure out what type of force molecules experience between each other by figuring out if they're nonpolar molecules or polar molecules. So nonpolar molecules exhibit dispersion forces, and polar molecules exhibit dipole-dipole forces. So for some of these molecules, you might need an electronegativity table. For some, you might have to figure out their geometry, especially if you have more than 2 atoms. All right, so I think we'll stop there for this video. In the next video, we'll continue on with the next intermolecular force.